So I am a geometer, and my aims in mathematics are using geometry to describe new structures and discover hidden patterns of mathematics. And in particular, I like very much bridging different aspects of mathematics. So here it will be differential geometry, probabilities, and algebra. So my talk is absolutely in this Poisson structures and symplectic manifold aspect of information geometry, but I'll have a totally different approach, and that's what I'm going to expose today. So let's start with the central object here, which are manifolds of probability distributions. So I recall this just in case someone doesn't know what is a measurable space and probabilities. I hope everybody does know. So that's briefly some recollections. And in particular, an object that I will be considering is the following. So I'll ask a measure to be absolutely continuous with respect to a given other measure lambda. And this is satisfied if for every measurable set A in F, so F is a sigma algebra, lambda of A equals to 0 implies that P of A, so the measure P of A is equal also to 0. And so from this is quite a strong statement because it implies the existence of a measurable function that I denoted rho here, such that P of A is the integral of A of rho d lambda. And I find this way of writing things quite interesting because, as you can see, we can write rho as dp over d lambda, which is the Radon-Nikodin derivative. So that's like just resumed in 2 words, the main object that will be discussed here in this talk. Okay, so now let's get acquainted with the manifold of probability distributions. So we consider omega f measurable space, where f is a sigma algebra. And we consider what we call a family of parametrized probability distributions on omega f. Yes, and the set of all probability distributions over a finite set forms a manifold. So last week I was giving a lecture on differential geometry in Sweden, so I recall a lot of elementary tools, and I thought maybe someone needs a reminder about manifolds. So quick reminder about charts, atlases, and coordinates. So everything starts naturally with cartography, and for example, Gauss wanted to make a map of the world, and well, it's natural to wonder how to do this, and that's how manifolds were born, actually. So the problem comes from cartography, and the question is it possible to draw an accurate map of a portion of our planet? So I took our planet, so as a sphere in R3 and an open set U, and we want to have something accurate that's going to, be a chart. So here, as you can see on the right-hand side, we should use this, it's called a chart or a system of local coordinates. Okay? And, okay, so now we can define manifolds and submanifolds, so that's the key object here. A topological manifold is a topological space M, such that each point P in M has an open neighborhood, which is homomorphic to an open set of an Euclidean space, right? That's locally behaving like some Euclidean space. And we need this second notion here of topologically compatible charts. So we can take 2 charts, phi 1 and phi 2, and we want the transition map to be a homomorphism. That's very elementary, but since, well, in the case of statistical manifolds, it's a little bit not so intuitive. It's always good to come back to things like that, in my opinion. Okay, so here we have different manifold types, and Particular, I am interested in the last one, symplectic manifolds. So we have coordinate charts in R2n, and transition maps are canonical transformation in the sense of classical mechanics. So here we have real analytic maps, and here holomorphic, the few morphisms. So I think within 2 minutes we covered the basics of, manifolds. All right, so now we can attack the central object that I want to discuss. So flat statistical manifolds of a given type, exponential here. What does it mean? So it means, in fact, that probability distributions can always be rewritten in that shape, okay, exponential of the sum theta I xi minus a given potential function. So it's incredibly important here. And this is for given chosen parameters, theta here, and random variables. So that's the type called exponential. And what we consider here are parametric families of probability distributions, what will be a manifold. And when I say flat, well, I mean the curvature is 0. So that's what I want to consider. I want to say also that all images have been generated by artificial intelligence, and that, it's sometimes interesting to see what artificial intelligence, how they see things. So, so that was my little introduction. And so let's start to be serious. What's new? So that's what we're going to talk about right now. Well, so let's start with a result that I had done in 2020 about flat statistical exponential manifolds. Well, I proved that they are so-called Frobenius. That means they satisfy a given PDE equation named WDVV equation, named after Witten, digraph Verlinde. So that's the one you can see here. So phi stands for the potential function, and G will be the, Riemannian metric in this case. And so what I want to add about this is that, the word Frobenius manifold was more of a geometric interpretation of what the physicists considered in the, 90s, WDVV. So it became a more elaborated notion of algebraic geometry called Frobenius manifolds. So this you can see in Riemannian's book on quantum cohomology and moduli spaces, for example. But historically, this was in fact coming from equations of hydrodynamical type. And in particular, this was developed by Novikov and Dubrovin. And so we're going to look a little bit at this side of the story, this hydrodynamical type of relation occurring here. So that's key object. Okay, and so that was development. So now let's talk about, so this was what we did in 2020, and now we want to talk about further developments coming from that side of the story, from that point of view, and including Poisson geometry. And I insist on my statistical flat exponential manifold, because otherwise it doesn't work, of course. All right, so let's get started. So the theorem is that statistical Frobenius manifolds form a Poisson manifold. So in the definition I chose, so that was just purely geometric. Poisson manifold is a symplectic manifold with some Poisson structure additionally there. And that's, I think, interesting because it relates, so as I said, a new point of view coming from this Frobenius manifold, this WDVV equation, two-dimensional topological field theory, to a theory that was developed here by Koszul, Souriau, and Winberg. So two different ways of thinking about the same thing. So I think this is really interesting to have a look at. It's like looking at the sides, two sides of a given mirror. You can see very different things maybe in different contexts, and we want to see how this all merges together for one object. So two theories, one object. Okay, so let's start about symplectic manifolds. So I started, well, in a very elementary way. So we have a manifold, I just recall things. We have omega and non-degenerate skew symmetric bilinear form on a given vector space. So this vector space is 2 n-dimensional. And the definition is that a symplectic manifold, so it's a smooth manifold equipped with what we call the symplectic form. So we have this condition that it is closed, which is necessary, and that it is non-degenerate, which means that that if omega xy is 0 for all y, then x has to be 0. So that's a very standard definition, and M has even dimension. So here I added a bit of a comment here about the linear maps. So I'm always considering something of finite dimension, because when it gets infinite dimensional, it's very hard. So let's keep finite dimensional, and in our case, therefore, this will give isomorphism. So we have a musical isomorphism, and this is the inverse here. Sharp is this inverse, Tm star is the cotangent space. And Poisson structure, well, there are different possible definitions, but I would just say this may be a very boring one. A Poisson structure on M is a bilinear map with Poisson bracket. Here we have smooth functions on the manifold M, and we have to satisfy a given number of properties, anti-symmetry, a kind of Jacobi relation, and a differentiation relation here. So that's Poisson structure, essentially. So how to look at how to prove actually the statement that this flat statistical exponential manifold is Poisson, and what's really happening regarding this TFT and this Frobenius manifold structure. So the steps are quite clear, I think. First we see that, So first we see that SFME is a symplectic manifold. Then we show that it has also Poisson structures. And for this side of the story, it's a little bit more complicated because we have to check it's an integrable system and equipped with some Hamiltonian action. So that's the plan. Okay. So let's attack the first step of the proof. So we prove that we have an integrable system. So, there are different ways of proving it. I think the most efficient one and direct is applying this theorem by Mahoff. The class of flat torsionless submanifolds in any Euclidean or pseudo-Euclidean space is an integrable system. And here we have good news. Frobenius manifolds are exactly manifolds which have flat and torsionless connection. They're flat and torsionless. So that's just perfect for our setting. In other words, the statistical flat manifold of exponential time forms an integrable system. And we're done. First step, done. Okay? And how about integrable systems equipped with Hamiltonian actions? Let's explore that. Well, here it gets a little bit more complicated. So let's explain the story. So there's actually a statement that says that the system has a Hamiltonian structure if and only if the Lagrangian L depends on the metric tensor. In other words, this equation here is satisfied, where G is the metric tensor, psi I, psi j are vector fields, U is just a scalar field, and X are, naturally canonical coordinates on the manifold. All this is illustrated on the diagram. And I want to say something related to my approach of the Frobenius manifold structure? Well, it's a very interesting story that happens here. So I like to think of the Plato's world of ideas, because we're catching some geometric ideas floating around us. And I want to say that there is a structure appearing that, well, I call the paracomplex structure. You can call it as you want, but the point is that we have an involution, a symmetry, which maps one submanifold here to another one. I drew it here in gray, E plus and E minus. So that's the involution. I squared has to be the identity, and we're working in a 2n dimensional space. So I called it paracomplex geometry. Other people call it hypercomplex. Choose the word you like. And if you don't believe me, well, I encourage you to check Paulette Lieberman's PhD thesis, because she describes exactly paracomplex structure. So this was done in her PhD, and, well, I found it again via another method. Okay, so let's get acquainted with paracomplex geometry. So paracomplex numbers I denoted with this Gothic C to imitate complex numbers, but it's not exactly complex numbers, because the generator here, epsilon squares, equals to 1 and not minus 1. So that's paracomplex, not exactly complex. But it behaves very much like complex. So if you have Z, which is X plus epsilon Y, epsilon is this generator, then you have a paracomplex conjugate, which is Z bar equals to X minus epsilon Y. So we can decompose the space into, well, paracomplex conjugates. That will be Z, and this is Z bar, for example. We can rewrite it always in that way. So I think that was an important side of the story, that we have this kind of paracomplex geometry occurring, and that given that it's not forming a field, well, we cannot talk about vector spaces. We can only talk about C modules. So we're working on C modules. J'ai plus de temps? Ou combien? Ok. D'accord. Ok, je vais aller vite alors. Very well. Let's go faster. So, okay, so the key information is to understand we have paracomplex geometry, and from then on, well, it's just a paracomplex geometry work to find the two form which will allow us to say that we have a Hamiltonian action. The Hamiltonian is a two form, and therefore we have proved that the statistical flat manifold with exponential type is an integrable system with Hamiltonian action. Right, so that was the summary. So we have this symplectic manifold here, this two form here, and we can talk about Poisson structures. So in particular, the secret relies in considering this manifold as a type of phase space, where, I think everybody knows what that is. We have one forms, paracomplex numbers, and function on the phase space, and these functions give us a structure of Poisson bracket here. Okay, and well, we can note that the Hamiltonian here is associated to this evaluation here. So this is for continuous case, and that's for discrete case. And that, well, we will define Lagrangian using this type of formula. So this works very well according to the fact that, well, the space is Lorentzian type, so we have SO1 and minus 1 in this case. Okay, so this is very standard calculation, the momentum, the force using Lagrangian here, and this allows me to write the Hamiltonian using L as follows here. So we have a Hamiltonian structure, and I'm almost done. So the corollary is that SFME carries a Poisson structure, and it is thus a Poisson manifold. And so I calculated everything using paracomplex numbers here. this is like more of a standard Poisson bracket. And well, just 1 minute, to talk about the hydrodynamical type. So I was saying, well, that Frobenius manifolds were related to brackets, Novikov-Poisson brackets of hydrodynamical type. So this is this impressive formula here. And so what I want to say is that this will actually classify, will be classified in terms of a Lie algebra, and that these elements here will be the structure constants of a finite dimensional algebra. In particular, if this is true, it's a Frobenius algebra, so it classifies two-dimensional TFT. So that's what I wanted to say essentially about Poisson, Frobenius manifolds of statistical type, and how they're related to TFT and WDDV equation. Thanks a lot.
Thank you.